All right, well then, let's not forget the material that we learned before, guys. You should always be in a stand that if the car comes to pick you up at night, you know, you are ready to board it, a black car. And by that I mean what happened during Stalin's time. You should always be prepared to pack your things and go. Limit as x goes to plus infinity, root of x squared plus 1 minus x. What is this limit about and how do we solve it? So one attempt will be to just plug in infinity. Infinity squared plus 1, square root of that minus infinity, and that's infinity minus infinity, which is 0. Would you tell me, please, if this is the right solution? Is this the right procedure? Let's see, who should I pick? So Mohammed, no, and David Wang, no, and Irvin Mo is saying no. And Stephen Lin is saying no. That's so nice. And what does Kelly Primiraj say? Good, and with big letters, no. Oh, very nice. Now, could anybody tell me why the answer is no? Oh, not the answer. Why is this the wrong procedure? Yes, please, guys. Why is this the wrong procedure? Stephen, so you say because we cannot just solve with infinity, but that's vague. You see, it already feels like you have floated far, far away from the shore. Why can't we solve with infinity? What exactly is the problem? Precision of language is very important. Muhammad, it's much better, but say more precisely, what is this symbol? What is this really infinity? Is this really infinity? Infinity is undefined, so one may be bigger than the other. It's still vague. I want you to, you see, guys, precise language reveals strong understanding. Imprecise language reveals that it's all muffled. The signal must come strong. Infinity is not a real number, okay, but why does it affect us? What is this infinity minus infinity thing? Infinity is an idea, but the idea has to be in your mind. If it's vague, then there is no idea. I can tell you what infinity is, but not enough of you bless me with your presence after class. Okay, let me remind you what this thing is. Language, according to Wittgenstein, has a significant effect on your concepts. In other words, the type of language that you speak will influence your thoughts. And that seems to be the case in this situation. We call it infinity and you start thinking about the wrong things. This symbol means increase without bound. So we are having a dynamical growth in our numbers here. So when I have what this means is that I'm squaring a huge number, adding 1 to it and taking a square root of that said huge number. So as I'm plugging bigger and bigger numbers, the quantity is exploding in size. Do you understand what I'm saying, guys? You see, it's a dynamic description. Like imagine, ooh, right, something is getting longer. The number is larger. And from this number, you are subtracting, from this calculation, you're subtracting, in that case, that same number. But here you square it and add 1 and take the square root, and then you subtract that same number. So there is always this danger that we are not taking account about how fast one quantity grows as opposed to the other quantity. Make sense? So for example, if you were earning $1 a day, but your spending is each day the square of the day. For example, so on the first day, $1 minus $1 squared, that's 0. Second day, it's $2 minus $2 squared. $3 minus $3 squared. You see, so the quantity that you're earning is increasing, and yet the spending is the square of it. So what happens is that the square is going to overwhelm and drag everything to minus infinity. You are only accruing debt. Does it make sense? So when you use this symbol, it belies the fact that we use the blanket umbrella word for one quantity that grows without bound and another. And when you have growth without bound, it's not like I'm subtracting a number from itself. It's really when I'm subtracting from an exploding quantity, another quantity that might grow at a different rate. And so this is vague. The answer ends up still being 0, but for a very different reason, guys. Always you should have this thought, multiply by the conjugate and simplify it. That's one possibility, right? Multiply by the conjugate and simplify it. Now, in this case, numerator simplifies to x squared plus 1 minus x squared. The reason we again multiply by the conjugate is we realize it's a minus b. And if I multiply it by a plus b, then I have a squared minus b squared. So I can possibly get rid of the square root and maybe it will be simpler. Does it make sense? Right? You can figure out those strategies. At the first and foremost, you have to know where you are going and what you are doing, right? And that's the Groundhog Day for me, guys. It's like I wake up and I talk to you, and it feels like, well, everything is erased. It's like the same day. It's 7 a.m. You know, have you watched this movie, right? I'm in actually a much worse Groundhog Day. It's a Russian Groundhog Day. It doesn't end well. There is a Russian Groundhog Day. It's called, in English, it doesn't translate well. It's called Зеркало для героя, which means a mirror before, it's annoyingly rhyming, a mirror before the hero. It's a great movie. I should possibly play you the first music and see if you recognize. You have to, guys, you see the reason that you are a blank square, one big reason, very upsetting reason, is that I imagine that information goes into your ear and there is no processing happening, right? If there is no processing, you are in darkness, and darkness is a terrible, frightening thing. You see, you have to have imagery, like in Hermann Hesse's book, The Glass Bead Game. You see, when you see imagery, when it connects to your prior experiences, to poetry, to music, to art, to imagination, then it's not boring. So then when I simplify the numerator, I get 1. Make sense? And then I have 1 divided by a denominator that clearly goes to infinity. And the answer, therefore, is 0. Good? The answer is 0. Now, on the other hand, tell me, what about this process? Can I plug, in this case, minus infinity in? And by plugging it in, I'm hoping that you do not forget what am I truly plugging. Here I'm plugging a number that is negative and large in quantity, right? So when I say x going to minus infinity, some of you, again, you're thinking about x, and some of your answers reveal there is an x at the end. And if you have the x at the end, it means you have not understood what is going on. This is saying we have root of a number squared plus 1. If I plug into this expression negative numbers of large magnitude, what am I getting? So I plug negative numbers with large magnitude, square plus 1. What am I getting? I'm getting a large number, clearly. It's large number plus 1 is a large number. Square root of a large number is also quite large. And then when I subtract a large number. So it's a large number plus a large number. And there is no problems here. It will be infinity, right? So infinity plus infinity is infinity. By that, I'm saying number that grows without bound plus another number that grows without bound, they together only contribute to the growth. They are not fighting each other. So it will be growth without bound, faster, bigger. Now, if you understood, please, very fast, we are behind. Solve this problem. The next one. Muhammad, but if we don't have to have the same result, why should there be the same result? At minus infinity, the solution is infinity. If you move to plus infinity, the solution is zero. The limit is zero. By the way, remind me, limit is zero. It means what about the graph? If I scroll my screen to the right for the graph root of x squared plus 1 minus x, what will I be seeing?
It'll get closer and closer to zero.
Yes, but what am I seeing? If I'm riding this train and I look out of the window of the train, what am I seeing? What is the landscape?
A curve that flattens out.
Exactly. It's a curve that flattens out at sea level. And it's basically, it looks like the x-axis. It looks like a horizontal line. Make sense? It's a curve that's flat. So we have a horizontal asymptote, and that's what all it means. It means that I am traveling along this one-dimensional yet infinite plane. For the previous problem, if x approaches minus infinity, the limit will be infinity, Zakia. Well, Zakia, when you see, here is what I want you to understand. It's not, there are no rules. There's no proper, non-proper. Do you understand what's happening when we solve it, right? Why was it improper? Sorry that I interrupt you guys. Why was it improper to plug in infinity in the first case and say the answer is zero? So, right, and we basically started saying limit as x goes to plus infinity, and I just plugged in infinity, and I have this infinity squared plus 1 root minus infinity. I get infinity minus infinity, and I said zero. Why was that not correct reasoning? Again, anybody? Nice to hear your voices too, by the way. Right? Just when you type it, it's just very unnatural. Would anybody like to speak? I want to hear that you have a voice. God damn it.
Hey, Professor. I don't think I'm finished yet, but so far I'm stuck at negative 3x over square root of 4x, 2 minus 3x minus 2x. I'm in a weird place.
You're solving the next problem.
Yeah.
And so it's root of 4x squared minus 3x minus 2x.
Yeah.
And first, what did you do? What's the strategy that you picked?
So I did what we did in the last equation, where I multiplied by the number over the same number, same equation.
So more specifically, what you do is it's called a conjugate, right? So you multiply it by the same thing, but with a plus instead of the minus.
Yeah.
And the reason being for doing that?
I don't really know.
because you look at the root, and then it's a match of pattern recognition. If you see a minus b, then you think if I multiply by a plus b, I have a squared minus b squared. That gets rid of the square root. Right?
Mm-hmm.
So it's really much of this subject is simply pattern recognition. And before I move on, guys, I am sorry again for the interruption, but one or two people said, why was it proper in the previous question to plug in minus infinity and say the solution is infinity, but when I plugged minus infinity, so when I plugged infinity, then the solution was not a proper way of thinking. Would anybody like to explain it again? I said it a few times. I want to hear, and especially so you understand, I would be very happy to hear from a person that feels that they don't understand it. If you understand it and you repeat it to me, okay, wonderful, you understood it. I do want you to be brave and speak to me when you do not understand. Guys, so am I speaking into the void? It does look like it. I see lots of black squares. You cannot imagine how irritating that is. And be careful, guys, right? So that's not a threat yet. But if I get the impression that you are not doing your work in this class, I will check you personally. I'll go one by one and I'll check that you are understanding the material. Okay. Thank you, Stephen. That's correct. Guys, so let me reiterate it as many times as necessary, is that this symbol is ambiguous. Language, and that's one other reason I do hope that you intend to learn another one, and I can help you at least with a few languages, is that you perceive the word differently by using different words, or by actually thinking more about what words mean. So many people say iron, and right away that means one thing for them. It might mean several things, right? And so here, so iron might mean the metal, it might mean the thing with which you are straightening the creases in your shirt. So similar with this symbol, it's not at all an infinity. This represents that, what is this saying? This is a quick way of saying that as I plug very large values into my function, I get a very large value minus a very large value. But it doesn't say which value is growing faster. You understand? This is just growth. I plug a larger number, this will be larger, this will be larger. But how much larger? So they are. It's not necessarily growing at the same rate. Does it make sense? right? So the answer does not necessarily equal 0. It could equal anything. It could be anything from plus infinity to minus infinity and everything in between. Is that clear? Write in the comments, please, Y or yes or something, so that I know I can move forwards. Yes, now you're saying yes, but then I don't hear your explanation, guys, and you stay black squares. Let's solve that other problem. So you see, because I actually, I can just see the answer right away to be minus 3/4. I don't even need to do any of the calculations. You do it. You do. I will explain to you later how I am able to accomplish it. But for now I am multiplying by the conjugate. It's called a conjugate. And the reason I do that is simply because I recognize this is A minus B. In other words, it's part of a product that if I simplify it, I can square this guy and I square this guy, and that might simplify my work tremendously. So it's A squared minus B squared. In this case, it's 4x squared minus 3x. That's the first part squared, minus this guy squared, which is 4x squared. When you cancel out, you're left with minus 3x. Now, this is what happens, what is on the denominator. Yes? Next, what I'm going to do, where do I get this x? I'm going to factor out an x from the denominator. Once I have a ratio, I want to simplify by factoring out the strongest growing power on the denominator, and I do the same for the numerator. So do you see what I do? I take this x. So first of all, I look into this bracket. Let me just add a few symbols in case that's not entirely clear. So what am I doing here? What am I doing here, guys? Well, I simply look at, so I have this root of x, and here I have, so it's x squared, 4 minus 3 divided by x. Yes? And then I can take this x squared and I factor it out. And I'm left with this x because x is here, it's positive. So factoring out of the root, x squared, it will give me simply, where did the minus 3/x go? Well, when I push the limit, it goes to 0. Yes? You understand how I accomplished it? So again, I factor it inside of the root, and then I factor it out of the root. So you see, that's just the algebra, guys, which again, you should know for this class. And if you do not know it, it's a sin not to stay after class and talk about it. So x is factored out. We can then cross it out and then push the limit. 3/x, x is large. It's a big number. It disappears to 0. So we're left with minus 3 divided by root of 4 plus 2, which is minus 3/4. Complete. Here is a question. I'm actually not going to give you time to think about it. And the reason for it is that I think if I give you 3 hours, you're not going to solve this problem. Most of you. Okay? It's too bad. I'm not sure if I already talked about it in this class, definitely in the other, but I wish we could just pause and I would let you to think about this problem for 3-4 hours to see what you will do. Okay. And the reason I would have liked you to do that, I want you to feel on your skin why understanding is so much deeper and better than just doing some sort of stupid steps, right? Even if you for some reason think that this is not an amazing subject. Right? It is exactly aligned with your ability to be efficient and not spend any mental energy on this unnecessary mental energy, on the subject. And that comes from only understanding. So the answer here, guys, you see, let's see how fast can I think of it, right? I'm not looking anywhere. I haven't checked this. If you believe me, this question, let's see how fast can I figure that out. So it's minus 5 on the numerator divided by 3 times the cube root squared of 8, which will be cube root and then squared, which would be 4. So it's 3 over 4, 12. So it's minus 5 over 12. That's it. Am I right? Yes, I am. The shortcuts are through here. Okay. Why did I solve it so quickly? Because not only did I go again, oh my God, let me just hammer the nail in. Let me figure out what's so to pick the answer. I actually think about what is this question about. You understand? So you are rushing around. Oh, the answer is 12, 13, 17, right? What does it matter? Do you understand what the question is asking you? And do you recognize what it is? Right now, it's just still early in your development here for calculus. You don't recognize what this limit is, and the book will not teach you how to do this recognition, but I will. Okay, so this is the derivative in disguise, right? It's just like the same thing with I put a mustache or I put a finger under my nose, right? Do you recognize it's still me? It's a very, very complicated problem, right? Some computers, especially when you develop, you do this. My God, what is this object, right? What is it that you do that you recognize? How do you figure it out? If I cover my eyes like this, is it still me? Can you imagine? Do it to babies. It's an amazing thing that people are able to accomplish. Extremely complicated. But the ability to recognize is specifically what you have to train. And if you train it, the entire subject looks to you like this, like one problem. It's just the same annoying repeated problem. Very simple. Now let's talk about an early morning paradox. Okay, one more thing about infinity that I would like to speak to you, and then again let's return to derivatives. So the most famous paradox perhaps about infinity is Zeno's paradox, and if you were in my classroom, I would have said that you simply cannot leave the classroom. You cannot stand up and go out. And of course, I would like you to feel that in your heart that you cannot leave me. But this is what Zeno said. So why can't you get out of a room? Because, well, to get to the door, you have to walk half the distance, correct? But to walk half the distance, you had to walk a quarter of the distance. But to do that, 1/8 of the distance. And to do that 1/16, and then 1/32, and on and on. In other words, to make any sort of step, to get to the door, you have to execute infinitely many steps. And many of you would say, well, that's ridiculous. I'm not sure about but you have experienced walking out the door quite many times, right? Rather a number of times. And therefore you think that perhaps, well, the paradox is somewhere wrong. So before I continue, I would like to know, guys, so type in the comments, if you believe this argument. In other words, do you agree with Zeno that you cannot walk out of the door? Simple question, and answer truthfully. You don't agree? And that's very interesting. You see, guys, so Irvin says, yes, I agree. I really want you to think about it for one moment. And my point is, I think, let's see, in the next question, I want to see if you would actually be with Zeno. You understand? I mean, in this situation, you say, or some of you say that you don't agree. I think, at least I commonly see when I ask the second question, that you will agree with Zeno. And logically, they are exactly the same, or at least we can talk about it. Okay, so let's have this universe creation experiment. So pay attention. In this experiment, the universe is a vacuum, as they say in Hebrew, tol vavo v'choshech al pnei tehom, v'ruach Elohim merachefet al pnei hamayim, which means chaos and darkness over a precipice, and the Spirit of God floating over the water. That's how the Bible begins. I still remember. So everything is completely dark, and then we have stars, which you can imagine, if you want to imagine, they're like billiard balls, so that you can actually say, well, this is a particular star and there's another star, and those stars begin to appear in the universe. There are 1, 2, 3, 4 onwards, right? Integer many stars, so a million, trillion, etc. So here is how the stars will appear in this universe. Half a minute before 12 a.m., stars 1 through 10 come into existence, with star number 10 immediately vanishing out of existence. And here is the illustration. This is the universe. Star number 10 is no longer burning. Does it make sense? It's no longer a part of the universe. That's the best way to say it. It just disappeared. How many stars in the universe? Well, clearly there are 9 stars instantly, 1/2 minutes before 12. Do you agree with me? Now, 1/2 squared minutes before 12, stars numbered 11 through 20 pop out into the universe. And star number 20 is immediately extinguished. How many stars then? That's 1/4 minutes before 12. We have 9 times 2 stars. Here they are numbered. The other stars are no longer part of the universe. They were expired. Good? What happens 1/2 cubed minutes before 12? Well, the next batch of stars, 21 through 30, come into existence. 30 immediately extinguished. So we have 9 times 3 stars in the universe. Good? Guys, so far, are you clear with what's happening here and how the time frame is structured? Can you guess what would be the next step? Step 4 will take place at what? Yes, Stephen. Everybody understands, or because the answers are not floating? I mean, are you still conscious? Is your oxygen level in your house good? Should I call 911? So here is how I can describe. You understand what the n means? I can describe it in one swoop, all the steps. 1/2 to the power of n minutes before 12. The stars numbered 10 times n minus 9, all the way to 10 times n, will come into existence with star 10 times n immediately extinguished. So there are going to be 9 times n stars in the universe at step n. That's the important part. Yes. So step 1, there are going to be 9 stars. Step 2, there are going to be 9 times 2. Do you understand how this is allowing me to quickly explain what happens at any moment of time? Right. So people are sometimes confused by this n, which is a strange thing. It's just you are generically speaking about all the steps at once. So here is my question. Question 1 is, exactly at 12, how many stars will be in the universe? Exactly at 12. So let me know, please. So Stephen, and again, I'm not sure, guys. I still haven't developed the ability to pass through the screen. You should not be afraid of me. So Alexa, you see you rolled 10 times n plus 1, but n is a meaningless thing, right? N is just, it's generically what happens at step n. There is no n. It has to be something else. And Irvin, here you go. But you never get to 12. That's an excellent point. Keep it in mind. It would be cool, guys, to hear your thoughts. And if you are misunderstanding something, let me help you with it. So Hu Wang, for example, what do you think? How many stars are in the universe at 12? And that's a very open question. Yes, just asking you, how many stars do you think are in the universe at 12? It keeps going on into infinity. In other words, what you're saying that even at 12, the number of stars keeps growing? But it didn't reach 12. Okay. Interesting point, Hu. Thank you. And you, Gabriel, what do you think? Gabriel Rios, you are there, correct? And you, Kirill, would be interesting to know what you think. And Yusuf Hassan, what do you think? Always, if you are there, just let me know as well that you are there. So before, guys, so being sure, it's another thing. First question is everything understood how this is progressing, right? Do you realize what's the relationship to Zeno's paradox? Would anybody tell me what's the relationship to Zeno's paradox here? What's the immediate thing that we relate to Zeno's statement about the room? Christopher says that we can never get to 12. Okay, so let me again show you why it relates to Zeno's paradox. You see, what did we divide here? We divided space 1/2, 1/4, 1/8, 1/16. We divided space into infinitely many segments, of course, not of the same size. What have we done here? We have divided the arrow of time, this 1 minute, this 1 minute distance into 1/2, 1/4, etc. And you see, so logically, the way you picture the arrow of time and the arrow of space, you picture them as the same thing, like this. Okay, so if time is in that sense similar to space, and then you should also believe that you cannot reach the door. If you believe that you don't reach 12, you should believe that you do not reach the door. You might argue that I'm not correct. You might say that time is a totally different thing from space. That's also a possibility. And so you understand what you are saying. If you say you cannot reach 12, it's not silly. So guys, it's rather underwhelming. Your reaction is this void. It's about many things. And it's a very silly, simple paradox in a sense. You understand that the more interesting things, just to even explain them, will take 10 years. All right, so everybody understood this procedure, correct? So we are basically, there are actions being taken every, first of all, half of a minute, then half of that, then half of that, then half of that. So at 1/2 to the power of 1, 1/2 to the power of 2, 3, 4, etc. So maybe I primed you too much. So many of you said that you cannot reach 12. Okay. So any other answers? So cannot reach 12 or any other answers? Because I will answer it once I talk about experiment 2. I will answer the questions together. Okay. Okay, I presume that you understood it. Let's go to experiment number 2. A very similar procedure. 1/2 minutes before 12, stars 1 through 10 appear, but the star that immediately is extinguished is star number 1. Yes? Then 1/2 squared minutes before 12, the next batch of 10 stars appear in the universe, but the star that expires is star that's number 2. Make sense? How many stars do you have at 1/2 squared minutes before 12? How many stars in my universe? Type in the comment. Well, 9 after first procedure. After second experiment, 1/2 squared, it's already 9 times 2, guys. It's not always useful to say 18. 9 times 2 is more useful because you are trying to see the pattern. You see? Because we're not going to stop there. It's 9 times 2. Because what happened? At this procedure, 1 star expired, another 10 stars were born. So a net gain of 9 extra stars with each step. Good? Now here is 1/2 cubed minutes before 12. The next batch I write which they are appear in the universe, and star number 3 expired. We have 9 times 3 stars in the universe, and in general that's the idea of n, right? So see, Alexa, so when I say n, it's like I'm saying human, or pretty much any blanket term that should refer to every particular step. So step n means that what I think when I say step n, I imagine this to be any integer. So what happens at step 5? I just plug instead of n5, and I know what happens in step 5. I plug it here, anywhere in here, and then I know what exactly happens. Yes. So for example, at step 5, stars numbered 10 times 5 minus 9 all the way to 10 times 5, that means to 50, appear in the universe. So stars 41 through 50 appear in the universe, and star number 5 is expired. So step n is truly supposed to talk about all the steps that I have and will have. Okay. I just wrote step 1, step 2, step 3 so to help you notice the pattern. But really, if I said step n, that's enough to describe all of them at once. So so how many stars do we have in my universe at step n? We would have 9 times n stars, because with each step I gain an extra 9 stars, right? So 1 is lost, 9 is gained. And so the question is, how many stars in the universe at 12. This time, it's for the second experiment. So if you could, guys, once more, maybe you write 2, 1, and you know, so write something like this. Let me show you. Maybe write something like Q1 and answer, and then Q2 answer. Okay, so this way I know what is your answer any different. It could be the same for both cases. It could be that you say that you do not reach 12, anything you like. Okay, it's in some sense that's what you do. You just muse this problem. You try to just play around with it in your mind and let me know what you think. You see, ping ping, when you say 1/2 to the power of n, it is meaningless, because 1/2 to the power of n is the time. It's just an arbitrary step. I need to know, there's no n, you understand? So 1/2 to the n is just, you're talking about all the steps at the same time. So Joshua, interesting point. So you say in question 1, it's infinite, but in question 2, all the stars stop existing. Kirill, Q1, the number of stars at 12 is infinity. Okay, that's for question 1. Likey, infinite, still infinite because the negative growth in infinity is smaller than the positive growth in infinity. Interesting point, Lakey. Thank you so much. It's infinite, that's Steven now, because we don't even reach 12. Well, if we don't reach 12, then at each step it's a finite value. Okay, so I would like to wait a little bit longer to have some of your, I want to see more of you guys. Well, So infinity minus infinity, what does it mean? And Dragon, when you say since it's infinite, Americans use the word it's just so much. It's. What is it's? Precision of language. Do you know? Just tell. Or just think. What does it refer to? The number of stars formed in question 1. So Kelly, you say infinite, no stars. Interesting, Kelly. Very interesting what you say. And I again don't remember who else. I think who did say that? Joshua Lim, I think, also said something like that. So Maya Hossein, infinite 2 is also infinite because the numbers soon disappears. Unclear for 2, the reasoning the number soon disappears. What number disappears exactly, right? So Edwin, infinite Q, they'll keep extinguishing at 12, or you mean so in question 1 at 12 they stop extinguishing, but at question 2 you're saying they will somehow continue to extinguish, maybe, if I understood you correctly. Okay, guys, how do you answer such questions? So first, let's address the time. So some of you say you will not reach 12. Okay, and that was Christopher, at least of the people that I recognize. So that's very, very interesting what you say there. I think that that first of all, when you picture the arrow of time, you know, you've seen the bar, right? It's just the same arrow time bar as it is for space, right? So the space is you have a ruler and you have a ruler for time. So this is just another rephrasing of Zeno's paradox. I think that if you believe that you cannot reach 12, then you also believe that you cannot exit the room. That means that you do not believe in motion. And so that you understand that that is not an entirely stupid belief. Right? So for example, but you see, that's not the way I thought of this problem. And one reason for it is that I remember, well, I remember a quote from Akujava. What do you think of time? Does time care what you do with it? It doesn't seem to, correct? I mean, some of you are just playing with your phones. I cannot see what you're doing. Others are sleeping. Or others are enjoying some book that they are reading, or hanging out with friends. That whatever you are doing, does time react to it? According to Bulat Akujava, and again, you should learn Russian. I mean, I do wish to at the end of this class to have the lecture entirely in Russian. А время торопит возница беспечный, и просятся кони в полет, which means, and time is hurried by a careless driver, and the horses ask to go forwards. That means that the time is not just sitting still or paying attention to what you are doing. It just seems to go uniformly. It's your task, or the task of, if it's God or whatever else is happening here, to carry out the procedures as instructed, right? The time is just moving to 12, and you have to actually do something, right? It's not intuitive, in my opinion, that time will react to what you are doing, correct? Time, its job is to go forwards. It is you, not time, who is placing the stars in this universe. At this moment, something is deity, whatever you like thinking, makes those stars pop in the universe, and time should not care about it. However, if you actually move objects around, that is the realm of the theory of relativity. You cannot move things faster than the speed of light. And let me ask you this question. If, let's say, you are going to travel on a rocket ship to a star that's located, let's say, 100 light years away from here. 100 light years away, it means that it will take light 100 years to reach that destination. Yes? You board a spaceship and you start flying. How long will you experience the flight? How long will it last? If you just sit there and you say, oh goodness, right, I have to fly this 100 light years. How long will the flight feel to you? Any ideas? Let me know. Alexa says seconds. Okay, that's maybe a good guess. So what about the rest of you guys? No idea? So for people watching this spaceship move, it will appear to take 100 years. But if you are sitting in this spaceship yourself, it will be instant. You will be there right away. It will not take any time to get there. Time will freeze. So on a deeper sense, maybe time does react to what you are doing. If you are moving very fast, time will slow for you. Good. But that's rather complicated here, and I can imagine the stars appearing in the universe without any motion. You understand? They're just appearing, just popping out, so that there is there's no idea of carrying them in or speed, so that I can try to imagine what's happening here. So then here is how you try to think. You try to think always like a monkey, very simply, right? So here is a jar. How do you know there is something in the jar? So I just wait until 12. You understand? I mean, all those metaphysical complexities I will try to ignore for a moment. I have this jar, and I want to, as a monkey, I want to know if there is something in it. If you're saying infinity or anything, is there something in it? Well, what do? I put my hand in the jar and I pull it out. So in experiment 1, will there be something that I can pull out at 12? Seems clearly so, because in experiment 1, I have star 1, star 2, star 3, right? So I can possibly pull something out. How many things could I possibly pull out? Well, definitely nothing that is divisible by 10, because the number 10 disappeared after first procedure, the number 20 after second procedure, 30 after third procedure, correct? So I cannot pull any star that has a number on it that's divisible by 10. Everything else I can pull out. Therefore, I would have said that the answer is infinity in experiment 1. Now tell me, what would I have said in experiment 2? What would the answer be according to me in experiment 2? It does seem to me, based on Zeno's paradox, guys, that you do reach the door, right? So at least you can divide space all you want, but it's just people just think, why is it such a paradox in Zeno's case? It's because they think that you have to execute infinitely many steps, but I don't see why dividing the distance means that you execute infinitely many steps. You do pass through infinitely many points, but there does not have to be infinitely many steps. Time is not required to carry out those steps. In the second experiment, you might, of course, feel like any machine. You can, let's say, how many push-ups can you do? Maybe you can do 30 or 40 or 50, but you cannot imagine doing 1,000 or 1,000,000, or definitely not infinitely many things. You cannot imagine accomplishing infinitely many tasks. It doesn't mean they are not accomplishable. That's a different story, right? But time, when you say time doesn't reach 12, intuitively it doesn't seem that time should care about what you're doing. Time's job is to move forward. Even though, again, so you understand, I'm not dismissing that you say it will not reach 12. Perhaps nature does seem to react to what we are doing. Definitely when we move faster, time slows for us, according to the theory of relativity, at least. You understand? So when you think about it deeper and deeper and deeper, of course, you're in the rabbit hole. I mean, it's complicated to say anything, but that's why it's useful to think very simply, like an animal here, right? So what do you have here? You pull. If you can pull something out, then it's in the jar. So in experiment number 2, my question is, can you pull something out of the jar? So Steven says yes. If I can pull something out of the jar, let's say in the jar there are only stars. What can I pull out of the jar? Can I pull star number 1 out of the jar? No, because it was eliminated after first procedure, correct? Can it be star number 2? But it was eliminated after second procedure in experiment 2, right? Remember that in my new setup for experiment 2, first procedure eliminates star 1, second procedure eliminates star 2, third will eliminate star 3. So it cannot be 3. Can it be 4 or 5 or any number? So if it's a millionth number, it was eliminated by the millionth procedure, if we reach 12, of course, right? So that means that in the second experiment, the number of stars in the universe is 0. So notice what's happening in both situations. So the heavens are becoming brighter and brighter and ever so faster, right? Because you have 9 times 2, 9 times 3, right? Faster and faster you gain extra 9, extra 9, extra 9. So the sky is brightly lit, but you reach 12, everything vanishes. That's the difference between limit and the actual, because we're dealing here with actual infinity. In experiment number 1, we actually have an infinity, not something that strives to be infinity, right? If you take limit of 9 times n, as n goes to infinity, that's as we accrue procedures, the number of stars we have is gained. But by 12, everything stops. In experiment 1, you have every single star whose number is not divisible by 10, it continues to exist. And there are infinitely many numbers that do not divide by 10. You understand? Infinite because it's not finite. That's what infinity is. You can define infinity to be a collection that's not finite. We can talk about it if you are interested. I'm not sure how much you are interested, but you should be very interested. Good? Now, have I shown you? It's on my channel actually, right? So I have other pictures elsewhere, but you see this picture? Do you know what it is? Yes, but this particular picture. I mean, all of those things, they have particular meaning that I placed here. That, by the way, is Heinrich Heine's poem that I illustrated here. And what is this? That's my auto-portrait. In my universe, you do not move anywhere. And because my universe is very scary and very sad. But one of them is I speak to you, and it's like, it's every semester when I teach this class, and it's like your accumulators, they go out. It's like everything that I placed in, or it's like water coming out of a jar with holes at the bottom, right? And I don't want the water to come out, truly, right? I really want it to be. I just want to plug those holes. I want it to stay. I want you to have this knowledge, to love it. And that's why I stay so late writing this nonsense. So here is the last of this experiments that I would like you to try to understand, right? And it's just very metaphorical for my life, right? So I am this bug moving in this one-dimensional universe from point A to point B. Okay. Now, so that you understand, simply imagine that you are watching this on YouTube. And if you prefer, maybe on just like you can imagine it on a two-dimensional screen, I can deform that, but imagine it's on a new stretchable screen. So you know, so let's say that this video, so that you're not bored, lasts only 1 second. This bug will go from point A to point B in 1 second. You understand? Now, imagine that the screen is very flexible. So you can stretch it all you like, deform it all you like. So if I were to stretch this screen, it will also take 1 second. Do you agree? You have experience of that, right? You can stretch a video on YouTube, it will play for the same duration, correct? Right. So any stretch of the screen will play for the same duration. Good. Now I'm going to deform the screen in 2 dimensions and still imagine it works. Okay. So here is how I'm going to deform the screen. I'm going to stretch and make a fold in it. in such a way that basically you see that I divide the screen into 3 parts. So here is part 1, this was part 2, and part 3. And what I do is I stretch the middle part to twice the size, and I fold it so it's like this. Make sense? So now what's the length of the screen? It's 1/3 plus 1/3 plus 1/3 plus 1/3. So the length of the screen is now 4/3. Am I right? So please tell me, how long will the video play? So this bug, the bug doesn't really care, or I do not really notice that there was a fold. My space is just a one-dimensional space folded in a two-dimensional superstructure. Good. So how long will it take this insect to walk from point A to point B, please? In the video. Well, again, if I stretched 1 second, if I stretch the screen, it's only a stretch that's visible to you, not to the bug in some sense, right? Because it's like a video. Have you ever tried to make a video longer, guys? You can, you can open a YouTube video, you can stretch it like this, or you can compress it, and the video will play the same amount. Do you agree with me? Look at it. You understand why I'm saying this is 1 second? Right, because it's only a stretch that's visible to you not living in the side of the space. This video still plays 1 second long. Good? You follow? The way I set it up? Now, what I do next is each of those segments of the interval, I kind of partition into 3 parts, and I deform the middle part to be twice as long. So this is of length 1/3. Partitioning it into 3 parts means it's 1/9, 1/9, and 1/9. Agreed? And then the middle 1/9 I make twice as long. The middle 1/9 I stretch, make it twice as long. So it's now 1/9 plus 1/9. So the total length here is 1/9 times 4. So 4/9. Good? And I do that with every other of the segments. So I do it here, 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 and here. My question is, what's the length of this new screen? What's the length of the screen? Can you calculate it fast? You don't need to add. I mean, that's a stupid way of doing it, but you can right away tell me what's the length of this new screen in your two-dimensional superstructure. So yes, Muhammad, it's 16/9, because the effect essentially is that I multiply each side by 4/3. You see that? 4/3. It used to be 1. 1 times 4/3 is my new length. Okay, and then you can see that this was multiplied by 4/3, right? That you would get if you have 1/3 multiplied by 4/3, you will get 4/9. So you multiply essentially everything by 4/3. You can distribute. You know how I know that? Because this times 4/3, it's 1/3 times 4/3 plus 1/3 times 4/3 plus 1/3 times 4/3 plus 1/3 times 4/3. I can factor out the 4/3, and I just see 4/3 times 4/3. Am I making sense, guys? Do you see how I right away know it's it's 16, so it's 4 squared over 3 squared? And don't worry if you don't, just talk to me. All I want is to communicate. Am I getting to you guys? I don't see enough of you answering it. Yes, let's repeat it. So the effect, the screen used to be of length. Here, let me possibly write it for you, right? So how do I know this? So what happened to the screen in first procedure, right? So the middle interval was made twice the length. So what I have here is 1/3 plus 1/3 plus 1/3 plus 1/3, which if I write in factored form, it's simply 4/3 times 1. Yes. In the next situation, this is 4 over 3 times times 1/3, and all of them are the same. So plus the next one is also of the same type. It's 4 over 3 times 1/3 and onwards, right? So the net effect is that I simply multiply the previous length by 4 over 3. Is that clear? And that gives me the new length. Make sense how I know it? It's again, this is what you have foiling. That's when you understand numbers abstractly, then you understand why that happens. It's 4 over 3 times 1/3 plus 4 over 3 times 1/3 plus 4 over 3 times 1/3 plus 4 over 3 times 1/3. So if you factor 4 over 3, you have 1/3 added 4 times. So it's 4 over 3 times 4 over 3. Good. And then you do the next step. The next step is each of those segments you again divide into 3 subsegments, and you make the middle segment to twice as long. What's the length of this curve now? What's the length of this screen now? You don't have to give me the numbers, right? You know, some number to the power of something. Right? It's not so important what the number is, because that's not finished. The screen is not complete. So it's 4 over 3, but drag on 4 over 3 to the power of 4. Or to the power of 3, my apologies, right? It's 4 over 3 to the power of 3. You see, we went like this. 4 over 3, then 4 over 3 squared, and that would be 4 over 3 cubed. Does it make sense? The effect of doing this procedure is to make the screen longer by a factor of 4 over 3. How long will it take this bug to move from point A to point B if my screen now looks like this shape? Assuming it can, of course, work. How long will it take the bug to move there? In other words, I take this space, I twist it inside of a 2-dimensional space. How long will it take the bug to get from point A to point B? You said you understood it before. Well, maybe I've used a few people say it. Yes? One second. Not per 4 over 3, because it's the same deformation. If you believe me from before, that no matter, if we agree that no matter how we stretch the screen, the video will play the same way. You understand? I'm just folding the paper. Imagine it's not a paper, it's a rubber band. So I can, or maybe Play-Doh. I can stretch it indefinitely and fold it, and it can still. You don't need to imagine a video. It just maybe it's simpler for me to explain it this way. You see? So the bug is just moving. For the bug, it's just a straight line, the same straight line, same space. You understand? It's like when I make a drawing, right? You make a drawing, I fold it. Whatever is on the drawing does not notice that it was folded. That's the way you think of it, right? So when you speak about about spaces, the space being twisted, you mean something like this. That's why you imagine it to be so. Okay. So can you guess? So it's 1 second. Can you guess what is this distance if measured in two-dimensional space? What is the distance from point A to point B? Not over here, but you see, you continue doing it every time. You continue deforming it, deforming it, deforming it. It's called the von Koch curve. Let me show you. This is the way the curve looks with more iterations. Do you see it? Yes. Good. So and then you have on top of each of those star structures, you have more of them. You zoom in, you have more and more of them. Can you tell me what do you think is the length of the end path? Once I finish construction, what will be the length of that screen? You must not have awakened, guys. Infinite, exactly. It is infinite. What do you think is the length from point A to point C? So in two-dimensional space, it's just a short distance. But what is it in my folded space? What do you think it is? Yes, Christopher, it is infinite. So this distance from here to here, and from any point that you pick, no matter how close, the distance is infinite. Do you understand? So this is Zeno's paradox, but in another form. It's something that is rather perplexing. You see, in this form, the length as measured in two-dimensional space between this point and that point is infinite. Between any 2 points is infinity. Any 2 points you pick here, the distance between them is infinite. Can you understand it? It's very simple, and this is specifically my existence. You see, so I'm talking to you. It's again. It's yeah, exactly, Christopher. That's exactly right what it is. I don't know. Do you still remember what is the derivative? All right, so new lecture. I'm not sure how fast we will go through it, guys. If you are not studying through this class, if I have to explain everything every day from scratch and you don't stay after class to talk to me, we're not going to get anywhere. And the exams will still be the exams, you understand? I mean, it doesn't matter what we get or not. I mean, the semester as a whole will be eaten. Again, if you do not understand, do not leave this classroom. Get the presence of mind to come to the next lecture if you need to rest, but do not go, right? Just I don't like that you forget everything. I don't like that you don't think about this material once we are not together. I don't like that I stay at night writing this thing and you are not spending anything on it. The derivative as a function. So what you do, and it's very important here, right? So what unit is it in the book? It's called the derivative of the function. I think it's 3 point something, 3.1. But then you have the notes, right? So you just you can see what it is in the book. You can just see the there's a list in the chapters. So the derivative as a function is this. What are we trying to measure? Do you remember what's f prime of a? What that's supposed to do? This is supposed to measure the slope of a tangent line. And what's the idea of a tangent line? We take 2 points on a curve, and we want to find the tangent line at point P. You see, here is the other sliding point Q. Here I drew lots of those lines. The sliding point Q, I will move closer and closer to P. And could anybody tell me, why am I kind of doing that? Why am I moving the point Q closer and closer to P? Why does it help me find the tangent line? Would anybody care to remind me?
I'm sorry, Professor. What was the question?
The definition of the derivative. I would like somebody, and again, guys, if it's somebody that doesn't understand, it's even better, right? I would like to hear from people that do not understand. I'm not sure why you're ashamed of that. What's shameful is that you don't care. That really irritates me. If you don't understand, I'll explain a million times. If you do not care, then you irritate me. What's the idea? Philosophy is what I want to hear, right? What's the idea behind this this limit? You see, f prime of a equal to limit as x goes to a, f of x minus f of a over x minus a. What is this expression supposed to capture? So slope at a point, but why? So what's the philosophy here? Okay, Aryan, brilliant. You want to connect the 2 points, but why do you want to connect them? Yes, as 2 points get closer, so very simple idea here, right? So if you have 2 points, between 2 points, you can draw a line. If you have 2 points, then you can construct a triangle that has hypotenuse, the segment connecting those 2 points, right? Has as a hypotenuse the segment connecting those 2 points, correct? And the similarity of the triangle, which we call slope, the ratio of the vertical leg of the triangle to the horizontal leg of the triangle, is going to be true for any triangle that you form for the same line. That's what we talked about it in the previous lesson, correct, guys? I hope you can visualize it. So that's what the slope is capturing. It captures the inclination of that line. Now I need 2 points to calculate the slope. Now, when I want to construct a tangent line, and even that we talked about, you remember, I hope, why that might be an interesting problem. It's extremely, just many interesting ideas have a lot in common with the idea of touching a curve, right? One of them is if you are trying to pick a chick in a bar, you can say, baby, let me be your derivative, so I may lay tangents to your curve. So trust me, there is nobody here that is indifferent, I imagine, you're still young, indifferent to the tangent to the curve problem, okay? So, you see this? And the idea is we take 2 points. 1 point is P, the 1 point where I want the tangent line. The other point is Q. Here is Q. And those are now 2 points. Through them, I draw a line. This is a secant line. Ah, Joshua, you want to know the pickup line, but you have to go to a very good bar, you understand? You can use it on Russian girls if you like them, if they're smart, right? Definitely the old aristocratic Russian girls used to be smart, right? So the line is very simple, not my line, by the way. I don't pick girls like this. I actually haven't been picking girls for quite a long time. But no. So the reason, because you see, I'm training to run fast, but you know, they're young, they are running much faster. That's what I used to do when I was a young college student. I used to run after them and quote them poetry until they collapse, and then you eat them, right? But I started, my legs are not as good, right? I can run a long distance, but that's actually what one of them, it's just, but they run fast. Okay, so So, so again, what was I saying? Oh yeah, so just tangent line, right? Let me lay tangents to your curve. Let me be your derivative, so I may lay tangents to your curve. Good. And what it means is that you select 2 points, right? And that is now a secant line through point P and through point Q. If you make point Q closer and closer to point P, it's like you are collapsing the 2 points into 1 point, and the tangent line is like a line that pierces the curve through only 1 point. That's what you mean by touching. I imagine a bullet grazing the curve, right? So if there is an entry wound at P and an exit wound at Q, the bullet pierced. And if the bullet just pierced at 1 point, it's like it just grazed you, good? At least locally, good? So this is at P. So there are 2 definitions. So guys, before I continue, is it all entirely clear? And if you need to, we can, if you really are tired, let me know where we can take a short break or we can continue. I do not know how much are you able to process, right? You are not talking to me much today, so it's just getting quite bad. I don't see enough comments. So type in the comments break or you want a 5-minute break or you want to continue quickly. I don't want to. I'm still good. So some people say 5 minutes break. All right, I will give you a break and hopefully, you see, we will continue. I will have to recycle the 5 minutes. Okay, so if you cannot stay afterwards, then whatever. My God, I lost some people already. All right. Let me pause the recording. I'll play you. All right, let's get back to our task. It's, in my opinion, guys, those things are all connected, right? What you listen to, what you think, what you enjoy, has a lot to do with how you perceive this material as well. So the tangent line. We have several notations that are mathematically equivalent, yet psychologically very different. So the first is this definition, right? So the derivative, this is called the derivative, it's just the slope of that tangent line. And this is what we calculate here. You see f of x minus f of a over x minus a, that's the slope between point P and point Q. And the reason we take x going to A, because that will cause the point Q to slide towards P. I hope that makes perfect sense to you. So you have to visualize it. You have to visualize the philosophy, and then this is simply capturing it in writing. Now, the other definition can be as follows, right? So notice that if x goes to A, denominator is vanishing to 0, correct? Denominator is vanishing to 0, so I might place a box about the denominator and call it h. And then what is x? X is the same thing as x minus a plus a. You agree? I just subtract and add something. And so what I see here is also h here. I say I put it in a box, I see here h. So x going to a, you know, x gonna give it to you. Maybe that's what I should have played for you. Maybe that would wake you up, right? Since that's what you like. It's not a bad song, by the way. I heard it in Rick and Morty. All right. Should I play that to you now? Would it wake you up? Would it cause some response? So this there is this h here and on the bottom. And so you have limit as h goes to 0 of a plus h minus f of a divided by h. Good? That's notation number 2. We will examine how they work in a moment. So there is the third notation, it's Leibniz notation. And this is df dx at x equal to a, or dy dx. And this is a very suggestive notation because this notation reminds you of the derivative's humble origin. Just as I said, just because the derivative moved to the Hamptons, it's not less of a peasant. It's the common slope. And if you remember that, it will not fool you. You see, so in how important is notation? Just a slight mention of what happened is that Newton and Leibniz, they quarreled over who was first to discover calculus. They accused each other of plagiarism. And of course, the continent means Germany, but Germany was not united, right? It's basically the Germanic people and then the English people. They sided with their respective scientists, and this notation caused the fact that it was not adopted in Britain. It caused a 50-year delay in progress. So, in 50 years' time, the continental mathematicians were ahead. You know, just they were ahead by as much as 50 years ahead of what was happening in England, and all because Newton's notation was this prime thing. That's Newton's notation, right? And Leibniz notation was this thing, dy dx. That means small difference in y divided by small difference in x. Here I try to illustrate. Here is that triangle. Here I made it large with a magnifying glass. This is dy, this is dx. Essentially, when you take the limit, you can in real life not push q truly to p. You stop when you think q is really close, and then you have a tiny triangle. Then you have a tiny vertical over tiny horizontal, and that will be a very good approximation to the actual tangent slope. That makes sense? So that's what you do when you if you actually had to carry the measurements. You don't know what this curve is. You don't have formulas for it. What do? You take this point P, and then you take another point. You draw it, and then with a ruler carefully you draw this right triangle, like I have here. It would be tiny right triangle, and then you connect you have this line. You can measure the slope of this line. You understand? It doesn't matter if it's tiny or not. As soon as you have this point, you can connect it with a line, and then you have this supposed tangent line for which you can measure the slope. Okay. So here is our task. Let's see which notation is better. So I would like you to right away, and do it as fast as you can, use notation 1. Notation 1 is the way we define the derivative. It's this notation. Yes. Use this notation to find the derivative of this function at an arbitrary point A. You see, you can solve it right away for all of them. Go ahead, please do it fast. All right, as you're thinking, I'll be back, okay? Well, I'm back. So, okay, I see some stuff, minus 4x plus 5. I have a feeling that some of you have taken calculus before and are using shortcuts, which are meaningless unless you understand why shortcuts work. Okay, so let's do this problem together. Are you there? Because you're saying it with x, the answer is not in terms of x, at least not in the way I wrote it, okay? So we want the derivative at some point a, good? Which means we're calculating the slope of the tangent line at the point a. What do? We need to pick 2 points. One point is x comma f of x, and the other point is a comma f of a. What's f of x? It's this, yes? Are you there, guys? This is my function, and this is the function evaluated at a. Next, what you do is you group terms, like terms to like terms. So you have 13 minus 13 is gone. Then you have minus 2x squared minus minus 2a squared. That just becomes in factored form, it's this. Do you understand, or do you need an extra step here? Let me know if you need an extra step, or do you understand how I do it, right? It's just basic algebra. I group things that look alike together. That's the idea of solving this problem. Extra step. Look at it. You see this? So we have this, and then we have this. We have minus 2x minus minus 2a squared. Together they make minus 2x squared plus 2a squared. And which I can quickly recognize. I can factor out the minus 2. So it's minus 2x squared minus a squared. Good? That's how I get this factor. Then I look at 5x and 5a. So it's 5x minus 5a, and I factor out the 5. Good? Good, so let's go on. So then what do I do next? Next, I factor, I need to get rid of the x minus a. So I factor the numerator. It's x plus a times x minus a. Here, I can factor out x minus a from the entire expression. Here I do it. Yes? And then I can cross it out. Yeah, I cannot do it before. So some people, they might right away, some people do this. They might say this and that. It's incorrect because you can only, what you're doing is multiplication pretty much, right? So it's really, in this form, look at it. It's multiplication times 1 over x minus a, which then I can cross it out. And so the answer is minus 4a plus 5. So when you say minus 4x plus 5, I always get the impression that you did it because you took calculus before. And if you took, you see, there is a point that I'm learning. Some of you think, well, I know a quicker way to do that, a shortcut. You're having tunnel vision. Okay, why were you not able to solve that exercise? Remember that I did before, that I right away guessed it was what, minus 5 over 12. I think I said, right? I right away could say it's minus 5 over 12. It's because I recognize certain things better than you do, and I recognize it better partly because of understanding and partly because of my experience doing the limit directly by hand. Okay, you don't use any shortcut until you understand why it works. That is not slowing you down, it's only slowing you down initially. It will speed you up tremendously. To me, the problems are the same. Why? Because I spend the time thinking about them. When you're just mindlessly, well, Zakia, there is no x. In my communication, I'm saying the derivative at the point A, the slope of the tangent line at the fixed point A. So x was striving to become A, right? X was striving to become A, but that's the setup, right? Here was the picture. This is A, and this is X. X becomes A, so it should disappear. X represents the horizontal coordinate of the sliding point Q. So that was the situation with the limit if I do it using this procedure A. Okay, I'm trying to show you something here. Do you understand procedure B? So in your book, and many people use that definition because some people open the book and see some examples there. You have this other notation. First of all, do you understand notation 2, guys? So it's limit as h goes to 0 of a plus h minus f of a divided by h. Do you understand this notation? Or do I need to go over it again? They mean logically the same thing. It's describing the same situation differently. So here you are describing the perturbation point, the sliding point, as very close to A. You see, it's very close to A, but there is a small error. Make sense? So here you're just calling it some extra letter. Here you're emphasizing that it's kind of A, but not exactly, with a small error. Right? And this is what it means formally. So using notation 2, you see this notation? Do you have the problem already written down, the question, right? So use the derivative, calculate derivative again, but now using the different notation, using notation 2. F of A is the y coordinate of the particular point at which we zoom in. It's always a matter of context, right? What is the meaning of x that you're talking about? What's the meaning of A that you're talking about? I said f prime of A, meaning that, you see, this means this is, I calculated the derivative at any point. If I said when x is equal to 0, the slope would be 5. If I said the point at which you calculate the derivative is 7, it will be minus 4 times 7 plus 5. Make sense? So I calculated the derivatives for all possible points. I don't have to use the formula again for different points. I know how all the tangent line slopes look like. And now I'm asking you to try to do the same with 2. If I'm not wrong, the usual class time is over at 12:05, correct? If so, then I will take another 5 minutes. If you cannot stay, then you can leave at 12:05. I mean at 1:05. That's very good, Kirill. That's exactly the point. I want you to feel on your skin, first of all, that they're not all the same, at least psychologically not. Yes, at 6:05, guys, I have the syllabi, and we're going to start with this lecture. So I do hope you come, and also you can stay after class. We can talk. We have office hours after this class, and we have office hours after the next class. Use those office hours. I have also a new system I can show you. Right, I can write. I now know what was the bug before. I can now write with my pen, so to speak. We can talk about anything you like. Again, guys, I'm sorry for interrupting you as you're calculating. I just hope you will not leave before you hear it. I do not care if you make mistakes or if you don't understand something. There is no reason you should hide it from me. I do get upset when you don't care. That's true. But if you care to understand something, I will do everything in my ability in my power to help you get it. I just want it. Leibniz notation, Alex, a very good question, but it is not it is not specifically useful for this problem. You will see how it's useful. Okay. Essentially, the equations 1 and 2 are the two definitions of the derivative, and I hope you understand how both of them are speaking about the derivative. Now let's solve this together because we're running out of time. This was factoring. Let's see what is the psychological thing that you do here. If you use this notation, look at it. You are expanding. You're expanding a bunch of parentheses, expanding, simplifying like terms, and then you still get the same answer. Okay. It's something that you need to feel on your skin. You need to solve many of them. Now, the question was, one person answered this question, which of the two procedures was harder and why? Would anybody like to comment on that? So Alexa, you say procedure 1 is harder. Okay. Why would you say that 1 is harder? David, very interesting, right? Well, I'm not sure. Seeing is one thing, right? So you can see everything in both questions. Now, if you count, how many symbols do you use, even at the very beginning? Yes, David. I would say that it's rather underwhelming, and unless you practice, you will not feel it. What's the situation? Let's see. For example, let's set up the derivative for a much more involved question. Okay, much more involved question. So you set it up using procedure 1, and just the setup will use 33 symbols. I counted them. Now, if you do procedure 2, the setup will use 43 symbols, 10 symbols more for just the setup. And as you're expanding and doing more calculations, the complexity will just grow. Yet you see, if you have to write, imagine you have to write 1 page or write 2 pages. One time, I mean, if you are a very quick writer, who knows, maybe you will be able to do it almost as fast. But imagine that that you have to do it again and again and again and again. So you do double the work at the very least. We will we will see that again. Okay, so it's very important which definition you pick. Even there it matters. Is that if you write more symbols, you are going to get to your solution slower. And also processing more symbols. If you have a program or anything, a good program is very compact. It doesn't involve many instructions, right? The fewer instructions, the better. The fewer symbols, the better. So very good, very well written programs occupy optimally little space, use optimally few symbols. Because even for a computer that can do things very fast, you see, if you have a slowdown there is a slowdown, it accumulates. Okay, so procedure 2 will at least on average will produce extra 10 symbols for, let's say, this question, right? Extra 10 symbols every time you write. So every line you write extra 10 symbols, and actually more, because when you are expanding degree 4 equations, let's say degree squared, degree 4, it will be more than that when you are going to expand it. You can, of course, treat it as you can actually do the same thing as you did in procedure 1. You can carry the same algebraic steps. It's just you are going to psychologically expand when you do this here. You don't have to, but that's what you do. I will actually possibly give you the time to do it next class to solve it again. But again, guys, I would like to say again what I see is happening. Well, first of all, I don't see much of it. Most of you are Malevich squares. You do not participate, you do not talk. I do not know or see or can gauge in any way what your reaction is. I imagine that you are just lying around like this, pretty much. That's what I imagine. Or watching the soccer game. I'm not sure if you watch soccer. Yesterday it was Bavaria playing. Right, and then your vessel has holes on the bottom, and it just flows, everything flows out. And we begin every lesson, we cannot begin from scratch. You have to be studying this material. You have to grab the bull by the horns. Do it now before it's too late. I'll stop the recording. Let's see if anything I said worked. How many of you are going to stay and ask me questions?